Hello, hey, this is Dr. Tech. I'm doing this recording for question number 1 of the final exam of the Wednesday cisp310 class in fall 2018. All right, that's very specific. I like that. All right, so with this question, it says right here in the table above, column address is the address of an instruction. Column code is the mnemonic of the instruction. B1 is the first byte of the instruction, and B2 is the second byte of the instruction. This is the implementation of the recursive Fibonacci code in the last homework assignment. So right here, I'm assuming that you at least spend some time to do the homework assignment. And if you did the entire thing by yourself, you would find this this particular question to be not too difficult, I hope, because it really is just a rehash of the homework assignment. Okay, so the code is incorrect. So right here, let me use the highlighter here. Highlighter. Okay, so it says here the code is incorrect, resulting in the following memory content when the program was interrupted. So what you do is you look at the memory content and you realize that something is not right about this. Particularly, there's a repeating pattern that keeps going backwards. The C code is not provided here, so you kind of have to figure out what the C code looks like, but we already know what the Fibonacci code looks like. So in order to figure out which value of Fibonacci we're trying to look for, you kind of have to decode the first part of the program here. Specifically, you look for the call to Fibonacci. So right here, the call to Fibonacci is, okay, let me go back to my pencil here. So the call starts with this instruction, which is a jump instruction to the subroutine. So the call is this part here. But in order to call, we have to set up a parameter, which is a value push on the stack right before the call itself. So you can see how this A here is being pushed on the stack because of the decrementality. So that means these three are here to push an argument of 6 on the stack before we call the subroutine. All right, so that tells us that we're trying to find the Fibonacci number of 6 according to the recursive version of the Fibonacci program. All right, so that gives us some context of what this question is asking. And then when we look at part A is asking what is the purpose of the byte at location 0xFE. So we need to count backwards. The 06 here, this is location FF. So location FE is referring to this byte here, which is 0C. But it's asking not what is the content. If anyone answers what the content is, that would receive no points because that's not what the question is asking. The question is asking what is the purpose of that byte at location 0xFE. There are several ways to figure it out. This one way is to read the program. So basically, by the time we get to this decrement, 6 is at location FF, and that's the argument. Okay, so if I want to annotate it, we can do that. So we can basically say because of these instructions here, location 0xFF is the argument, which is 6. And then the next byte being pushed on the stack is the return address. So these instructions here is pushing the return address here. Specifically, the address is 6 bytes after the LDI instruction. So if we start with the LDI instruction, which is here, and we add 6 bytes to it, that results in the increment D instruction. So this is actually the return address. And as a result, the correct answer to part A is that it is the return address. Okay, so we'll say this is the return address, but you have to specify to where. This is the return address to main, because there's another return address. Because if you look at part B is asking what is the purpose of the bytes at locations FC, FA, F8, and F6. Alright, so using the highlighter tool, we can highlight those bytes. Okay, so FA, so let's start with F6 first. F6 is referring to this byte here, is a 2-3. F8 is also a 2-3. FA is also a 2-3. And the last one is FC, which is also 2-3. So those are all 2-3s. So once again, there are two ways to figure out what that byte really is, or what is the purpose of that byte. Because once we get into a subroutine, okay, so let me scroll back to the code here. So once we get into the subroutine, let's try to analyze what bytes are being pushed on the stack. Okay. So once we get into the subroutine, and in order to find out what is being done on the stack, the key is only to look for instructions that would change register D. So this is one instruction that would change register D at location 1B. It decrements A, decrement D, and then we push something on the stack. And this is right before another call sequence. So when you look at these four instructions here, that's the first recursive call to Fibonacci inside Fibonacci itself. So now we, basically our question is, given that is the case, where is it going back to? Or what is being pushed on the stack? This is not the 2-3, because the 2-3 is the first instruction here. Okay, the first sequence of instruction here. So this part here is pushing n-1 on the stack. So this is the argument n-1. And then this part here is pushing the return address. So by the time we push n-1, that's where we see the 0, 5. Okay, let me change to the highlighting tool. So the 0, 5 is the argument. So that makes the 2-3, which is one location lower than the 0, 5, the return address to fib. Okay, this is the return address back to fib. So the answer is, this is the return address to back to Fibonacci. Now to be even more exact, this is to the Fibonacci. This is after the first recursive call. But that's a little bit specific, and if you just say it's a return address back to fib, that's fine. Okay, I did mention that there are two ways to figure out what part A and part B are. With part A, we know the content at that byte at that location is 0A. So one way to figure that out is really kind of to look at 0A here, and what we find, 0C, excuse me. So we find that 0C is this location, which is a return address. This is where we are returning to. There are two clues that this is a return address. Okay, one, that location is being pushed by the instruction at location 06. Okay, that's one. But the second one is there's no other way to go to location 0C because it's right after a JMPI instruction, and there's no label at location 0C, so we are not continuing execution at location 0C because of a JMPI instruction. It has to be done indirectly using a JMP instruction. So that answers part A and part B. Part C. The problem is the repeating pattern starting at location 0xF5. There are two locations that the program can branch to cause this. What are those two possible locations? Okay, so let's go ahead and find location FC first. And I'm gonna use the highlighter again, and this time we'll use maybe a purplish color. So the last one, this one is FF. So FFFEDCBA 9876, and this is the first one. So we are looking at the 06 being the starting point of the repeating pattern, and to be more exact, the repeating pattern consists of here all the way back to here. And if I were to use another highlighter, let's try blue here, you can see it has exactly the same pattern here. And if I use yet another highlighting tool, let's try orange, we can see it is also repeating here, and so on. So that pattern repeats a few times. The question is, what can possibly cause this to happen? There are several ways to work on this problem. One is you can actually emulate the execution of the program because it has a bug, and figure out that, oh, okay, we're having this pattern because that behavior of the program. If you did that, then you will find that it is branching to location 01 that's causing this to happen. But that does require you to kind of emulate the entire program, and you're possibly reading part D first, okay, because part D does give you a clue. But if you do not have time to do that, then the question is, what can regenerate this particular pattern? So we have to start with the known, we have to start with the facts. So the fact is, the repeating pattern is actually exactly the same as what it should be at the very top part of the stack, which is this particular pattern here. So if you look at this pattern, the 06 is pushed onto the stack using we investigated this already. So the 06 is being pushed to location 0xFF because of okay, I need to use my highlighting tool, because of this part here. It's because of the push instruction, and that's the only place we're pushing a 6 on the stack, followed immediately by the return address of 0C, which is done by okay, I'm just highlighting the curly braces here, which is done by that. So there's only one okay, let me see, two locations where it can be done like this. The first one is obvious. Okay, the first one is if we get back, if we somehow jump and continue to execute at location 02, that's going to repeat that pattern because this is the beginning. This is the first instruction that is going to push the 6 on the stack. We cannot go back to location 00 because if we jump back to location 00, that would have reset the stack pointer back to 0. So we would not see the repeating pattern in RAM because it's going to be overwriting location 0xFF down to location F6 repeatedly, and we would not be seeing the repeating pattern chewing up memory like the way it does. So it cannot be location 00. We know location 02 is the obvious location. The not so obvious location is location 01. Location 01, oops, let me clear that first. Location 01 contains this byte 00 here. That byte is not intended as an opcode. It is intended as the immediate constant of the LDI instruction. However, the processor doesn't really care what is the quote-unquote intention of a byte. If the JMP instruction gets to that location, it's going to treat it as an opcode. So 00 is the opcode of no op, NOP, no operation. So that means if we continue execution at location 01, we'll just be executing the no op instruction, which has no effects whatsoever. And then we'll get to location 02 and basically start with the push 6 on stack again. And that's how we can generate the pattern that we see in RAM. So to answer the question of part C, the problem what is those two possible locations? So the correct answer is location 0x01 and location 0x02. Those are the two possible locations. I'm hoping most people can get the obvious one, which is location 0x02. But location 0x01 is the other one that is possible. All right, so moving on to part D. Why do you think the program branched incorrectly? A hint is that the only bug of this program is missing the increment D instruction that is commented out after location 0x33. So the first thing we need to do is to find out which one we're talking about. So location 03 is here, and the commented out instruction is this one here. Okay, I was intending to use a highlighter tool, so let's switch to a highlighter tool. So the instruction that we are commenting out is this one here. That doesn't work either. Let me try that one more time. Okay. So the instruction that we are missing here, okay, that's a little bit too much, but it works okay. Is that one here. So missing that instruction, what is it actually doing to the program? We know the rest of the program is correct. So use that as a hint, okay? The rest of the program is correct. It is just missing this increment D instruction. It is supposed to be in the program, but it's not, okay? And the question is asking for an explanation why this missing instruction is causing the observed symptom, which is the repeating pattern on the stack that keeps chewing up stack space. All right, so I'm asking for an explanation. So the explanation is so we need to figure out what the stack is used for this program. We know the rest of the program is correct. So if the rest of the program is correct, then we know that this is supposed, by the time we have, okay, change the color back here. So we know this is supposed to be the stack pointer pointing to the return address, okay? So we know that at this point, D should be the address of the return address. Okay, and then we execute the program backwards. Okay, so by the time we get to location 3-4, so at this point, because the program is supposed to be correct, we know that A is supposed to be the return value. Okay, and it's adding B to A. Okay, so now we have to ask, where is it getting B? So it's getting B from this instruction here. A is the return value register, which means at this point A is supposed to be the return value of the second recursive call in fib. Okay, so if I were to comment here, okay, so at this point A is supposed to be the Fibonacci value of n minus 2, and if on line 34, or if at location 34 A is supposed to be the actual return value, we know that B is supposed to be the Fibonacci value of n minus 1. But now we have a problem, because you can see how at location 33, B is loaded from the stack pointer D, and then at locations 3-5, we're also loading the same byte into B. So what is that byte? Because that byte cannot be both the return value of the Fibonacci of n minus 1 and also at the same time the return address at exactly the same time. That just cannot happen. And that's why the increment D right here is important, because this one is supposed to change it. The return value of Fibonacci of n minus 1 is supposed to be pushed on the stack earlier, and now that we have used it, the increment D is supposed to clear that. But since we did not have that increment D that I use a pointer to draw, so what that means is now we have the same, the stack pointer is still pointing to the return value of f of n minus 1, or excuse me, n minus 2 when we get to location 35. So it's using the return value of Fibonacci of n minus 2 as if it is a return address. And that is why we are branching to the wrong location. So that is the reason. So the correct answer in this case for part D is the increment D. Okay, let's back up a little bit here. So the explanation for part D is the stack pointer is still pointing to the return value of Fibonacci of n minus 2 when we get to location 35. So it is mistakenly using the return value of the Fibonacci of n minus 2 as if it is the return address. That would be the explanation. And that's a little bit long, so I'm not going to write it. Instead, I'm going to type it here. So let me see if the typing tool works. Okay. Okay, there we go. So, so the return value of the Fibonacci n minus 2 is not deallocated, and it is used as the return address. And that's, that's kind of sufficient already. But then, if you want to know, okay, what is n at that point? Well, do we know what is n at that point? Well, we actually do. The reason why we know, what n is because when we analyze this code here, we can see that 0, 2 is n, and this is 2, 3 here. Oh, I take it back. Okay, I just figured out that I was wrong. The return value of Fibonacci of n minus 2 is in register A. So what the stack point is pointing to is actually the Fibonacci value of n minus 1. That makes perfect sense. And so to be even more specific, when n equals to 2, because when n equals to 2, neither of the recursive call is going to cause any further recursive calls, because n of n minus 1, which is f of 1, does not have any further recursion, and then f of n minus 2, which is f of 0, also does not have any further recursive call. It is the result of f of 1, or the Fibonacci of 1 that was pushed early on the stack, and that is being used as the return address when we get to locations 35, 36, and 37. And that's what causing the program to repeat that pattern in memory. All right, so this is kind of the answer to question number 1 of the final exam. And as I work on more questions, I will continue to post more videos. Oh, by the way, Merry Christmas if you if you're watching this on the 24th, which is probably unlikely.